The use of cannabinoids in medicine is becoming more common, but this doesn't mean that smoking some weed will solve all of your problems. In actuality, research in this field is only really starting to uncover the complex biochemistry that is behind the interaction of cannabinoids with the human body. We will learn much more about this later in the video. One case that exemplifies the medicinal potential of cannabinoids is the molecule cannabidiol, or CBD. CBD has been approved by the FDA last year for the treatment of 2 rare epilepsy disorders in infants. Patients usually have to rely on combinations of pretty strong anticonvulsants to get some relief. A study in 2017 looked at cases of drug-resistant seizures of the Dravet syndrome, so cases where standard medication didn't really help. They showed that the frequency of seizures per month could be decreased from 12 to 6 with the use of CBD in addition to other medication. Moreover, 5% of patients remained completely seizure-free. The treatment is, however, not completely risk-free, as they observe some side effects such as loss of appetite, fatigue, or diarrhea. In Switzerland, they even started selling cigarettes containing CBD for recreational use. Even though CBD is not psychoactive and it's legal, you're actually not allowed to smoke CBD cigarettes in Switzerland during your military service, which I find pretty fun. CBD's infamous psychoactive cousin, THC, on the other hand, is also used for the treatment of chronic pain and MS. Until recently, it was thought that cannabis was the only plant that produced THC. In 1994, it was shown that liverwort, something which sounds like it's taken straight out of a Harry Potter book, produces a cannabinoid that's structurally very similar to THC. Now, in 2018, the latest research demonstrated that this cannabinoid, called PET, displays some pretty interesting pharmacological characteristics, and the whole story has led to some silly headlines. We'll talk about this, and of course, some synthesis in more depth later in the video, so be sure to watch everything. This is going to be quite a detailed and interdisciplinary video. The video consists of 3 parts. Firstly, we'll learn more about the history of cannabinoids and how the father of THC got away with taking kilograms of cannabis from the police. We'll see how THC was essential for the discovery of various biochemical processes and pathways in our body. In the first part of the video, we'll talk about organic synthesis. You see, to enable the biochemical assessment of PETs and other unnatural cannabinoids, the scientists at Bern were supported by synthetic chemists at THCO in Zurich. Ultimately, a lot of the biochemical groundwork we'll cover relied on the use of highly potent, unnatural, and also radio-labeled cannabinoids. Of course, good old organic chemistry was there to help out. We'll also contrast this with the modern synthesis of THC. The active compound in cannabis. In 1964, the Jewish chemist Raphael Mekulam and his colleague Yechiel Gaoni first isolated and characterized THC. Just 1 year before, in 1963, they had already isolated and established the structure of CBD. The cannabis they used for the extraction of cannabinoids was actually supplied by the police. The Israeli police at that time had enough hashish that was being smuggled from Lebanon. The director at the Weizmann Institute, where they were researchers, had some friends in the police, and after some persuasion, Mekulam was allowed to pick up some kilograms. 1 year later, in 1965, Mechoulam and Gaoni published the first total synthesis of THC. We'll have a brief look at the key steps from the synthesis. They started with the reaction of the terpene E-citral with an aluminum species. After nucleophilic addition onto the aldehyde, the free alcohol was obtained. Now the alcohol was tosylated by treatment with tosyl chloride and pyridine at room temperature. Interestingly, this cyclic compound, which is basically methyl-protected CBD, was obtained in low yield after chromatography. How is this possible? Mechoulam postulated that there's an allylic rearrangement happening, converting the starting material to a disconjugated olefin. Then, intramolecular SN2 prime substitution leads to the formation of the six-membered ring. Now, with the desired double bond in place, just a few additional steps completed the total synthesis. The synthesis of CBD and THC, as well as a bunch of other cannabinoids, has seen significant advancements in the 20th century. Many of these methods rely on the use of terpenes as starting materials and include a lot of interesting rearrangements. Another approach, published 5 years after the first total synthesis by Mechoulam, involves a one-pot sequence. In this method, carene epoxide is reacted with dihydroxybenzene in the presence of boron trifluoride. In the first step, one of the three phenyl groups attacks the cyclopropane, which is ruptured due to a Lewis acid-mediated opening of the above sound. This installs the ether linkage. The second step is basically an electrophilic aromatic substitution here of substituents are strongly electron donating and activate the portal position for the intramolecular elation. The synthesis, structural elucidation, and new isolation procedures facilitated research into the pharmacology of THC and other cannabinoids in the 1960s and 1970s. This enabled our studies, the discovery of the ECS. In the mid-1980s, groundbreaking findings were made in Alan Howlett's laboratory at St. Louis University. This research provided evidence for a type of G-protein coupled receptor in the plasma membrane that specifically interacted with cannabinoids. This CB1 receptor is actually one of the most abundant receptors in the central nervous system. It was also demonstrated that CB1 is involved in a highly complex signaling pathway, influencing many enzymes that are key in regulating numerous biochemical processes. To give you an idea of just how complex these signaling cascades are, here's a modern overview of pathways of the anti-tumor effects of cannabinoids in cancer affect cell cycle proliferation, cell death, and tumor progression. CB1 is involved in pain, inflammation, olfaction, neuroplasticity, motor control, and the regulation of appetite and food intake. It's well known that THC increases appetite in users. There are various ways by which THC is believed to do this. THC increases the incentive motivational properties of foods, essentially eating pleasure and the palatability or tastiness of the food. In addition, THC also increases ghrelin levels, which is an appetite-stimulating hormone. Since activating CB1 increases appetite, it shouldn't be surprising that blocking CB1 has the opposite effect. This is the story behind rimonabant, a CB1 antagonist that was sold as an anti-obesity drug. The emphasis is on the was sold. Just after 2 years of its first approval, rimonabant was withdrawn worldwide. Although it was effective for weight loss, serious psychiatric side effects, including suicide, outweighed its benefits. By now, we know that CB1 is involved in various processes, so specificity is pretty difficult, and this can lead to severe side effects. Nevertheless, further studies into CB1 antagonists might lead to a breakthrough in obesity research. Novel antagonists with selectivity for CB1 receptors in peripheral organs may achieve similar metabolic results with decreased psychiatric adverse effects because they don't hit CB1 receptors in the brain. Rimonabant is still pretty useful for pharmacological studies, as we'll see later in the video. In 1993, Sean Monroe at Cambridge University identified a second type of cannabinoid receptor called CB2. This can be found in the peripheral nervous system, organs, and the immune system. Although their functions have similarities, the CB2 receptor shares only about 45% homology with CB1. It's important to note that the expression of CB receptors highly varies between different locations within a given tissue. A particularly interesting feature of CB2 receptors is that they appear to be highly inducible, with expression in CB2 increasing up to 100-fold following tissue injury or during inflammation. So it's not as simple as just having two distinct receptors. There are also different isoforms that drive specificity, allowing the endocannabinoid receptors to exert a wide variety of effects. Now, the question you might ask yourself is, why are there receptors for compounds that come from plants? A friend of mine once told me that it's because humans were meant to support the cannabis and get high. But these receptors actually exist for endogenous compounds produced in the human body. This system started evolving over 600 million years ago, so the plant didn't come first. The first example of such an endocannabinoid is anandamide, which was discovered in 1992. Again, good old McCollum was involved. The isolation of 0.6 milligrams of anandamide was the result of 2 years of chromatography and binding assays, starting from 4.5 kilograms of pig brains. Anandamide interacts with both CB1 as well as CB2 and plays a role in multiple processes. An interesting one is the following moderate intensity exercise increases anandamide levels significantly. It's believed that anandamide induces the mood-lifting effects of exercise, for example, the runner's high, by interacting with CB receptors in the brain's reward centers and leading to the release of dopamine. 3 years later, in 1995, McCollum and co-workers found another endocannabinoid, abbreviated as 2AG. Most people talk more about anandamide than 2AG, and I think it's probably because anandamide was named after the Sanskrit word for bliss, so people can call it the bliss molecule, and that makes it more appealing. In actuality, 2AG is present at much higher levels than anandamide in the CNS. The affinity of 2AG for the CB receptors is much higher, and it suggests that 2AG might actually be the more important natural ligand. Given that we have two similar but also different receptors, as well as endocannabinoids, the topic of specificity comes up again. Let's first think of how the body does this. There are some other endocannabinoids than the two guys we mentioned, but the toolbox is pretty limited. By a highly complex combination and regulation of dozens of factors, our body somehow still is able to elicit highly specific effects. Well, when you're trying to develop compounds in the lab that interact with the cannabinoid system in a specific manner, you can't just swallow or inject something that hits both receptors. That's why people have investigated specific binders. In some cases, like this J compound, the structure still looks like a cannabinoid. Others, like GW, aim for it to look quite different though. Why should we care about this specificity? Well, this compound exhibits potent analgesic and anti-inflammatory properties, but without the cannabis-like behavioral effects, as it has a low affinity for the CB1 receptor. So you might be able to treat things like chronic pain with it without getting your patient high as a kite. In summary, the research motivated by the cannabis plant has uncovered the vital endocannabinoid system. This system consists of CB receptors and endocannabinoid messenger molecules we've talked about, as well as enzymes that are responsible for the synthesis and degradation of endocannabinoids. The endocannabinoid system influences a myriad of processes, and some people call it the most important physiologic system involved in establishing and maintaining human health. Alright, so let's talk about getting high on moss. What is liverwort? And is it actually superior to medicinal cannabis? Because this video has been a total freestyle so far anyways. The key takeaway is that liverwort and cannabis are two totally different plants. Bryophytes are non-vascular plants. They lack supporting and nutrient transporting tissues, which limits how tall they can grow, amongst other things. Angiosperms, in contrast, the majority of plants do have such tissues and reproduce with flowers, seeds, and fruits. On the evolutionary timescale, bryophytes and angiosperms have been separated for over 300 million years. The remarkable result of convergent evolution is that these two different plants produce very similar cannabinoids like THC. This compound occurs in the plant as the imperiled carboxylic acid, which is decarboxylated during smoking or drying. So you can find liverwort species that produce paratatinin in Japan, New Zealand, Costa Rica, and Tasmania. Liverwort preparations are purchasable online and sold as a legal high. The online community reporting about legal highs both affirms and refutes the anecdotes regarding the cannabis-like effects. Now, Professor Burke from the University of Bern wanted to evaluate paratatinin pharmacologically. For the first time in the next part, I'm going to summarize the key findings of this research. If you want to know more than just my dumbed-down version, feel free to read the paper. In mice, the team demonstrated that PET reaches the brain relatively easily and binds to CB1 and CB2 receptors, but to a much weaker degree compared to THC. This means that liverwort doesn't give you the same euphoric high as cannabis, making it more attractive for medicinal purposes. The lowered potency also decreases the risk of overdose. The team also investigated the unnatural diastereomer transplant, as in the case of the THC scaffold, is a less potent binder than the transpiler. So far, we've only seen a quantification of the binding interaction. What is the macroscopic result of this weak receptor binding? There is a behavioral test called the tetrad test, which is employed to screen drugs that induce CB receptor-mediated effects in rodents. This tetrad test, as the name suggests, consists of 4 components. The first experiment is a measurement of body temperature, which can be decreased dose-dependently by cannabinoids. To get a reference, let's first focus on THC at a relatively low dose of 10 milligrams per kilogram. THC decreases body temperature. Okay, the same result can be observed for PET, albeit at higher doses. We've seen that PET is a less potent CB1 receptor agonist than THC, so this makes sense. The unnatural trans-diastereomer has a similar effect, serving as a kind of control experiment, if you will. They also tested the PET isomers in combination with another compound, here abbreviated as SSR1. Pre-treatment of the mice with this compound fully abolished the pharmacological effect of PET. Can you guess which compound this is? I'll give you a hint, we've already seen it in this video. It's our good friend rimonabant. Again, we might not use it as a drug against diabetes, but in this case, the CB1 antagonist is useful in demonstrating that the tetrad is dependent on CB1 receptor activation in the brain. Because pre-treatment with rimonabant occupies the CB1 receptors, pharmacological effects that would arise from PET binding are not present. The second experiment in the tetrad test is the measurement of catalepsy. It's measured by retaining the mouse in an imposed position with its forelimbs resting on an elevated bar. Catalepsy is the amount of time that the mouse stays immobile. PET also passes this test. The third experiment is the measurement of hypomotility, or in other words, decreased spontaneous activity of the mouse. You can measure hypomotility by placing the mouse in a cage with grid lines and counting how many lines it crosses during a certain time period. Essentially, you're measuring how much the mice move around. In this case, PET was tested with the rotorod test. You put the mouse on a rotating metal rod and test the time after which it falls off the rod. Here, the mouse is placed on a plate that's heated to about 55 degrees Celsius. The experiment measures the time it takes for the mouse to show a nociceptive response, such as licking its paws, shaking its feet, or jumping off the plate. In this experiment, mice treated with PET showed longer response times than the control group, indicating an increased pain threshold. So, with this part, I wanted to give you some insights into how the effects of cannabinoids are actually measured. Long story short, PET activates the receptors. However, it is a much weaker degree than THC so far. We haven't identified anything special, though you might think so. What it turns out, PET has a unique effect. You see, PET actually decreases levels of E2 and D2 prostaglandins. What does this mean? Well, prostaglandins are lipids with hormone-like effects that are involved in a variety of biological processes. In this case, lowering prostaglandin levels could mean that PET-like cannabinoids could have fewer side effects, such as memory loss and less neural inflammation. Forward, this could make PET-based cannabinoids ideal candidates for the treatment of chronic pain or inflammation. However, all this research is still in its very early stages. Alright, let's move on to the third part of the video and finally talk about some organic chemistry. What enabled the team in Bern to execute the pharmacological assessment was a supply of synthetic PET and its unnatural diastereomer. This was the work of Professor Carrera and co-workers at ETH in Zurich. That's what we'll jump into. The forward synthesis. Their route didn't start from a dihydroxybenzene like the other approaches towards cannabinoids we've seen so far. Rather, they started from 3-bromoanisole and subjected it to Suzuki coupling with this boronic acid. This reaction proceeds under standard conditions with high yield and installs the side chain containing the phenyl ring. Next, the crucial carbon-carbon bond was formed by allylation and quenching with acrolein. The allylic alcohol is obtained in excellent yield, as allylation is directed by both the fluoro and methoxy substituents in a synergistic manner. Also, the nucleophilic addition selectively proceeds in a 1-2 fashion. Next, the product was used in an alpha allylation of this aldehyde. This really is the key step of the synthesis. This reaction employs 2 chiral catalysts and installs the 2 cis stereocenters that are found in the product. The aldehyde also contains a terminal alkyne, which underwent intramolecular ring-closing metathesis using Grubb's 2 catalysts to forge the cyclohexene. Let's dive deeper into the emulation reaction, as it's really fascinating. This reaction is an example of stereodivergent dual catalysis. What does that mean? Catalysts are employed, and they generate 2 activated intermediates. In this case, it's the electrophilic iridium allyl complex and the amine derived from the aldehyde. These intermediates are both chiral, So this enables you to access all possible stereoisomers from the same achiral starting materials by just changing the stereochemistry of your catalysts. Remember, transmits the unnatural diastereomer. The team also tested pharmacologically. Well, simply taking the enantiomer of the amine catalyst is what allowed them to synthesize it. This really highlights the utility of stereodivergence, in this case for the preparation of unnatural analogs of biologically active molecules. Next, the oxidation stage at the carbonyl carbon was adjusted by converting the aldehyde to the methyl ester by pinic, oxidation, and esterification. Now both methyl groups were induced by a double Grignard reaction. You might not be very familiar with pinic oxidation, so as a little exercise, take a minute and write down a possible mechanism. It looks like you're throwing in a lot of stuff here, so what's actually going on? Chloric acid, so chlorine with oxidation stage +3, is actually a reactive oxidant. The chloride anion attacks the aldehyde and subsequently undergoes a parasitic fragmentation. Essentially, you're abstracting a hydride and thus oxidizing it to the acid. This reduces chlorous acid to hypochlorous acid, which itself is still quite reactive. To consume it, high excess, in this case 4 equivalents of a scavenger such as 2-methyl-2-butane, is added. You might have guessed that for substrates that contain other functional groups that are susceptible to oxidation, this reaction isn't the most selective. To complete the synthesis, the aryl ether bond was constructed by an intramolecular nucleophilic aromatic substitution. Interestingly, the outcome of the cyclization was highly dependent on the choice of base. While employing lithium or sodium hydride in refluxing only led to recovery of starting material, potassium hydride afforded the product in 78% yield. The final product was demethylated by treatment with excess sodium. The modern approach we've discussed before started with a 3-step sequence from this aldehyde in order to introduce the side chain. The reaction and subsequent hydrogenation of the olefin installed the saturated side chain present in the product. After demethylation of the phenyl groups with boron tribromide, this dihydroxybenzene was obtained. Again, the team used the inherent reactivity of the aryl ring to introduce a substituent in the ortho position, namely iodine, by an electrophilic aromatic substitution. After protection of the phenyl groups, the aryl iodide was subjected to a steel coupling with this organotin compound. So, after formation of the CC bond within the aryl ring, the stage was set for the construction of the cis-bicyclic system. The team accomplished this with a highly useful reaction, the Ireland-Clayson rearrangement. First, the secondary alcohol was used in esterification of this carboxylic acid. The acid also contains a terminal olefin, so you might already be able to guess which reaction this will enable later on in the synthesis. Now, the key Ireland-Clayson rearrangement installed 2 stereocenters with high diastereo selectivity. This closed transition state is why Clayson rearrangements are really useful in selective synthesis. We are already quite familiar with the underlying strategy. To finish things up, the carboxylic acid was converted to the methyl ester to allow a double Grignard reaction. Note that this also removes the benzoyl protecting groups, which makes sense because they are also esters. Then, a ring-closing metathesis forged a cyclohexene ring, just like we've seen in the Carrera synthesis. For all maybe 17 of you who managed to make it to the end of this video, I wanted to say thank you, as these truly do take a while to compile. I hope to do more in-depth understanding videos on the thought process of cannabinoid variety for the more astute student. It has been a blessing, a privilege, nay an honor to teach and consult with you today. See you in the next one.